If carbon-13 NMR is completely new for you, one general principle that I find helpful is to correlate proton chemical shifts with carbon chemical shifts by multiplying by a magnitude of 20 to get a rough estimate. And that's what figure 4.3 is demonstrating, where there is quite a bit of overlap in the proton and carbon-13 chemical shifts if you transpose by this factor of 20. The main difference is that for allylic carbons, the allylic carbons tend to be more shielded than what we see for the allylic protons. And for alkynyl protons, the protons tend to be more shielded than the corresponding carbon atoms of the alkyne. One big difference between carbon-13 chemical shifts and proton chemical shifts is that the carbon-13 chemical shift being on the skeleton is more predictable, whereas there are many effects on the skin of a molecule that will affect proton chemical shifts. In Chapter 3, the textbook presented Schulery's rules for predicting proton chemical shifts, but I find that those are not terribly useful for compounds that are moderately complex, whereas there is more confidence in being able to predict carbon-13 chemical shifts, even for relatively complex compounds. I've shown portions of a few tables from the textbook. Table 4.5, which I've shown just a portion of this, shows baseline chemical shifts for alkanes, and I've simply chosen the first 8 linear chain alkanes. Table 4.6 then shows how we can adjust these base values with a large number of substituent effects. There tends to be a deshielding effect for most substituents at the position attached or alpha to the substituent. In most cases, that deshielding effect falls off as we get further away from the substituent, and in some cases even has a negative value or a shielding effect as we get further away from the substituent. That gamma position or third position is rather interesting in the shielding effect of the substituent. On the carbon-13 chemical shift. Table 4.12 shows how substituents affect the chemical shifts of benzene compounds, starting with the baseline value for benzene at 128.5 parts per million. These are shown for monosubstituted benzenes. However, the estimates often will apply to multiply substituted benzenes. In most cases, the substituent has a deshielding effect. For most of the groups that I have shown, these are electron donating substituents. So at the ortho position, C2, and at the para position, these groups tend to be shielding, promoting more electron density at the ortho or C2 and para or C4 positions, providing an experimental manifestation of negative charge buildup from resonance or inductive effects. This is an example from a simple problem. In an exercise, we made a claim from the proton spectrum that the structure corresponded to nitropropane. We can also now examine the carbon-13 spectrum to further strengthen the claim. Beginning with the data from table 4.5, using propane as the base, these are the values for the methyl, the methylene, and the methyl group of propane, and then provide an adjustment from table 4.6 for the nitro group at the alpha position and at the beta position. These line up pretty closely with the calculated values, line up pretty closely with the observed values. The one deviation is that the methyl group of nitropropane is more shielded than the methyl group of propane itself. And that could be consistent with there being a shielding component at the gamma position, even though that is not provided in table 4.6. This was an exercise from the proton spectrum where we could make a claim of butan-1-amine, or common name butylamine. However, the proton spectrum allows us to really only assign the triplet A2 for the primary amine and the triplet E3 for the terminal methyl group. At this resolution, there is too much overlap for the 6 protons from 1.4 to 1.2 ppm to really assign them too firmly to specific positions. However, for the carbon-13 spectra, we can tell that A, B, and C are secondary or methylene groups, and that carbon resonance D is a methyl group or primary group. We can then use the baseline values from table 4.5 for butane, and then apply a correction value from table 4.6 for the amino group at the alpha and beta positions. Once again, these line up fairly closely between calculated and observed, the one exception perhaps being the gamma position, which is more shielded in butylamine than it is for the corresponding position in butane. The last example is for an aromatic compound. From the proton spectrum, we may assign the 2 hydrogens labeled A2, which are doublets, to be the hydrogens at 3 and 5 for a compound that might be claimed as 2,6-dichlorophenol. The triplet, a 1H resonance, might then be hydrogens at 4, and the remaining singlet, which is 1 hydrogen integration, could be the hydroxyl group of the phenol. The carbon-13 spectrum is more revealing. In particular, there is clearly a quaternary carbon at 148 part per million without any hydrogens attached to it. And then there are 2 carbons that each have 1 hydrogen attached at B and at C. The expansion also shows a very small peak, which is D. We'll come back and make a prediction about D in a moment. But if we apply the basic value for benzene, 128.5, and then add in the various substituents from this table for the phenol and for each one of the chlorides at the 2 position versus the 6 position. Now I'll encourage you to work through this, but the phenol is attached at 1, then there is a chlorine attached at 2 and another chlorine attached at 6. If we compare the calculated and observed values for this tri-substituted aromatic, at carbon 1, there is some deviation between the calculated and observed chemical shifts, but it's still fairly close for the chemical shift observed for carbon A. These values are quite a bit closer for the remaining resonances between calculated and observed. We can make a claim that D may be carbons 2 and 6 due to the very weak signal due to the absence of protons attached to carbons 2 and 6, due to the absence of one bond nuclear-nuclear Overhauser enhancements.